Hello, my name is William Chapman, and I'm a fifth-year graduate student in the Department of Earth and Planetary Sciences at UC Santa Cruz. I study geomorphology, or the study of landscapes and how they form. And more specifically, I focus on rivers, which are particularly interesting and dynamic features of Earth's surface. Rivers are incredibly relevant to humans. We rely on rivers for transportation, drinking water, electricity, agriculture, and more. But rivers also damage adjacent infrastructure through sedimentation and flooding. Of course, flood risk is different for every river, so it's important to understand which rivers pose the greatest threat to nearby communities. One way we can assess flood risk is to think about how rivers transport sediment. This is because the amount of sediment that's carried within flow influences the shape and behavior of the river channel itself. So, considering how much sediment a river carries at a given flow rate, in other words, the efficiency of that sediment transport, may tell us a lot about a river's natural hazard potential. Some past studies suggest that rivers in more arid regions have especially high sediment transport efficiency. However, this hasn't been demonstrated broadly using direct sediment measurements. So in my research, I am exploring whether there's a connection between climate and sediment transport efficiency by looking at records from dozens of rivers in the United States. To start, I selected 71 different U.S. Geological Survey stream monitoring stations with continuous flow records and measurements of suspended sediment concentration, or essentially how much sediment by weight is carried within a liter of water. The sites are shown as white dots on this map, which itself is colored by aridity, with warmer colors representing more arid locations and cooler colors more temperate. I wanted to quantify the sediment behavior at every site, so for each one I plotted the stream flow, or discharge, against the suspended sediment concentration, as you can see here for the Bad River in Wisconsin. I modeled sediment behavior with the following equation on the upper right. Suspended sediment concentration is equal to a coefficient k times the discharge, q, raised to an exponent a. The coefficient essentially tells you how much sediment there is at a given discharge. So for the sake of simplicity, we're going to focus on this value. However, just note that the exponent is also useful for describing sediment behavior, as it tells us how responsive the sediment concentration is to changes in discharge. So I plotted the coefficients and exponents for every single one of those 71 different sites on this graph here, with the exponent on the x-axis and the coefficient on the y-axis. And each of the sites is also colored based on the aridity at that location. There's a clear pattern here. We move from the blues in the bottom right to the reds in the upper left. So in other words, the rivers in the more arid locations tend to have a higher coefficient and lower exponent than temperate rivers. So in effect, this means that arid locations with those really high coefficients transport generally higher concentrations of sediment compared to temperate rivers for a given flow rate. This work advances our understanding of connections between sediment transport, flood hazards, and climate. And projects like this will be particularly important when considering how river behavior will shift in response to climate change. I'm hoping that my future work exploring why this climate and sediment relationship exists can further inform our understanding of river behavior in a rapidly evolving world.